Hi everybody. Hopefully this is a relatively quick video about pendulums. Um, you've done this experiment where we figured out, which factors kind of influence the period of a pendulum. And you figured out that the mass of a pendulum really doesn't matter, doesn't affect the period. You figured out that the amplitude of the pendulum really doesn't affect the period, but the length does. Why is this? If you look at the equation for simple harmonic motion, the period that we kind of derived, um, it's equal to 2 pi times the square root of m over k, which leads you to think, well, the mass should matter. Why doesn't the mass matter, and why does the length matter? Hopefully we'll get to the bottom of that by the end of this, but before we do, check this out. I want you to realize that when we say a pendulum moves in simple harmonic motion, it's only an approximation. Simple harmonic motion is a linear motion. Notice, as I make the angle that the pendulum goes through bigger and bigger, the less this is truly simple harmonic motion because there's an up and down component as well as a side-to-side component. So when we say that a pendulum moves in SHM, that's really only an approximation. In fact, the bigger this angle gets, the less the approximation is valid. So keep that in mind. Everything that we do here is going to work for small angles of theta. How small? Well, the smaller the better, I guess. This is a nice diagram of a simple pendulum. What makes it simple is the fact that the mass is concentrated into a point at the end of a massless rod or massless string. If the string or the rod had a lot of mass relative to the bob here, then it would cease to be a simple pendulum and it would oscillate differently. So one thing I'm going to need to do in order to derive an expression for the period of a pendulum is to get a diagram showing the displacements and a separate one showing the forces that act on the bob. Remember that the period of a simple harmonic oscillator is this, and this is sort of generic. This is for any simple harmonic oscillator. But like I was saying earlier, why doesn't the mass matter with a pendulum? Well, it must have to do with the k value. This is indeed valid for a pendulum. It's just we need to know what the k is for a pendulum. Remember, k is the force constant for simple harmonic motion. It tells you, how many newtons of restoring force there are pushing this thing towards the center for every meter of displacement from the center. Restoring force is minus kx. We need to know what k is for a pendulum here. So we'll get to the bottom of that. As far as the displacements go, let's say that here's the pivot, here's bob. Let's call this L. That's the displacement from the pivot to bob. And this would be the y component of the displacement. This would be the x component of the displacement. And this is the angle theta. As far as the forces on bob, we've got a tension force pulling directly towards the pivot. We've got the weight of bob pulling straight down towards the center of the earth. And that's really it. Now, since this tension force is at an angle, let's draw on some axes here, I could draw its components. So if this is Ft, that means this is the x component of Ft, and this is the y component of Ft. Once again, this is theta. Now, here's an approximation, a couple of approximations actually. As long as theta is small, here's a couple of things that are pretty close to being true. As long as this is a small angle, the hypotenuse is going to be very nearly the same length as this. And as long as this is a small angle theta, there's not a whole lot of up and down motion of this thing. That means there's really not a whole lot of unbalanced force up and down. In other words, mg is really close in size to the y component of the tension force. Now, these are only true if theta is small. The bigger theta gets, you can imagine, the less and less those are true. If I want to derive an expression for K, let me solve this for K. Now, I can kind of dispense with the negative sign here. The negative, remember, it only tells you that x, the displacement, is in the opposite direction of F, the restoring force. And that kind of shows up on our diagrams here. Here's x, the displacement, to the right. Here's the restoring force, to the left. So if I want to put in vector notation here, I can drop the negative sign and do that. Okay. And I could drop that because this vector is assumed to be to the left. This vector is assumed to be to the right. So going back over here, here's where the mystic voodoo begins. This triangle, I could write this expression. The tangent of theta is equal to the opposite side over the adjacent side. So it would be x over y. But remember, y is approximately L when theta is a small angle. So I could further say x, our horizontal displacement, must be equal to L tangent theta. Keep that in mind. Now let's go over here and do something similar. The tangent of theta here has got to be equal to Fx, that's my horizontal restoring force, over this side, opposite over adjacent, which is approximately mg. So I could rearrange that expression and say my restoring force, Fx, is equal to mg tangent theta. Now, keep these two in mind, and let's go back over here. Try not to write off the edge of the screen. K is equal to the restoring force over the displacement. And I know the restoring force is this. So let me just substitute mg tangent theta. And I know that x, my displacement, is equal to L tangent theta. So tangent theta cancels, because whatever theta is, the tangent of that would cancel. So K for a pendulum is actually equal to mg over L. Now if I take that and put it back into our expression for simple harmonic motion period, K is this, m over mg over L. Now that expression simplifies a bit. What do you know? Mass cancels. So when you did your experiment and figured out, hey, this pendulum that weighs twice as much doesn't seem to affect the period, it has twice the mass, why isn't it affecting the period? That's why. K itself for a pendulum, folks, depends on the mass. So if you increase the mass, yeah, you've increased that, but you've also increased K. So in the end, the mass cancels out. K gets bigger as the mass gets bigger. Now this is a denominator in a denominator, so let me further simplify and say 2 pi L over G. So here's where we're at. This expression applies to any simple harmonic motion. This expression applies to simple pendulums only. Okay. The L is the length of the pendulum in meters. G is the acceleration due to gravity, which you can round it off to 10, or you can use a more exact value. Or if you were elsewhere in the universe, it might be a different value. So here you go. That's why the length matters, but seemingly there's no x in here. The displacement doesn't matter. If you pull it further to the side, it doesn't seem to affect the period a whole lot. The mass doesn't seem to matter either. But keep in mind, disclaimer, this entire thing was sort of predicated on small angles of theta. For big angles of theta, the less accurate this is going to become. And another thing that's an approximation, we said this was a massive bob with a massless string or rod. The more mass is in the string versus the bob, the less accurate this expression is going to be. So we always kind of assume simplifying things. Those are the simplifying things we've assumed here. Hopefully this helps you to understand the period of a pendulum.